Okay, so good afternoon everyone. In this second half of this lecture discourse on optimal control theory and solution of optimal controls via calculus of variations, I am going to look at problems involving constrained optimization and mainly with the introduction of the Hamilton-Jacobi-Bellman equation. So, today's topic of discussion will be the following. We have the Pontryagin, we are going to look at the constrained minimization or also known as the Pontryagin minimum principle, also known as the constrained optimization, or I am going to denote this principle. We will see what this rule is, denote this by the rule PMP, and I am also going to discuss our derivation as well as the use of Hamilton-Jacobi-Bellman equation. Notice that this equation will be very similar. So, this equation will be very similar to our Hamilton-Jacobi equation HJB. Okay. So, let us recall some of the concepts that we have covered in the last class. Mainly we have done unconstrained optimization, that is unconstrained minimization via the introduction of the Hamiltonian or the Pontryagin H function. Okay. So far we have done unconstrained optimal control, and we see that for this setup we form, I am going to quickly recall our solution methodology. We form the Hamiltonian H, which is equal to x bar u bar lambda t, which is v of x bar u bar t plus lambda times f of x bar u comma t plus, well, so in general lambda is a vector. So, where lambda I define it as my co-state function, right, or the Lagrange multiplier, and then so we solve for the optimal control problem. We solve for the solution of this form. So, partial h partial u at starred condition is 0. So, this is for our control function, and then we had also two inequations, partial h partial lambda is set equal to x bar dot, this is also at starred condition, and finally we have, so we have partial h partial x with a minus sign, this is at starred condition, is lambda bar dot, this is also at starred condition, right. Okay. So, the first equation is my control relation, the second equation is my state relation, which gives me my state vector state relation, and my third equation is my co-state relation, which gives me my Lagrange multiplier. Notice we have one relation given for the control, we have n relations for the state relations, and we have n equations for the co-state relations, right. Okay. And so, and plus we also had the natural boundary condition, which are partial s partial x minus lambda, this is times, so this is star times delta x f plus h plus partial s partial t at starred condition times delta T f, right. So, this is set equal to 0. So, this was in summary our total the total methodology of solving our unconstrained optimal control problem. So, now suppose on top of that we place some restriction, or we have some restriction on the control variable. So, then how to approach such a problem? So, this question now is, suppose we place restrictions, on controls, on our control function, let us say u bar of t, and let me denote the restriction as the maximum value of u cannot exceed, let us say the maximum or the magnitude of the control function cannot exceed a certain quantity. Suppose we place this particular restriction, or component wise what I see is the following: uj minus less than uj of t is less than uj plus, right. So, uj minus is less than equal to uj of t is less than uj plus, right. So, component wise we have the following restriction. So, now we cannot assume anymore that the variation in our control function is arbitrary. So, we now cannot assume that the control variation delta u is arbitrary, right. So, we cannot assume that the control variation delta u is arbitrary, and so which means what shall we do in this case? Now, notice that so far we have been optimizing our performance index or functional by setting the first variation equal to 0. The moment we have a constraint on the control variable, we cannot set the equality condition, but certainly we would like the first variation to be non-negative, right. So, the idea is the necessary condition is now changed as follows. So, the necessary condition for u star to minimize, j will be the first variation partial j of u star comma delta u is greater than equal to 0. So, no longer we can assume an equality. So, we have to assume an inequality. Okay. So, let me call this condition as A, and so what have we got? So, we can now break down this condition A into two parts. Suppose we fall back into our unconstrained case, or our optimal u is found by taking the derivative, or it is within the constraint, then this inequality reduces to the strict equality. Otherwise, if the maximal or the minimal u or the minimal control is found on the boundary, then we have to solve the inequality. Okay. So, what I have said is the following. So, A is valid if my optimal control u star lies on the boundary. So, this is the, so we have to check the boundary values along with the interior values. So, it lies on the boundary or is constrained, right, right, or and in this case, well, so it satisfies A star, or the other issue is that the first variation is 0 if u star of t lies within the boundary, u star of t lies within the boundary or has no constraints, constraints. Okay. So, what have we got is that we can use our regular conditions that the first variation is 0 if u star lies within the boundary, or there are no constraints on u, which is unconstrained problem, or we can impose the inequality if u is constrained or u lies on the boundary. So, let us look at this sort of a problem. So, recall that my first variation was as follows. The first variation of the performance index was del j at u star comma delta u. This was integral T 0 to T f of partial h partial x bar plus lambda dot of delta x plus partial h partial u times delta u and plus. So, this was all the variations that we had, partial h partial lambda minus x bar dot times delta lambda, right. So, this was the last one was the state relation, the first one was the Euler Lagrange equation, and the second one was the control equation, right. And then, so this was all the integral over dt plus I had partial s partial x bar minus lambda at the start condition and evaluated at T f times delta x f plus h plus partial s partial t evaluated at the start condition and T f times delta T f. So, that is my the last two expressions are my natural boundary condition. Okay. So, recall that when we were setting the first variation equal to 0, we had 1, 2, 3 and 4 conditions set equal to 0. So, now we are again going to set all but one condition equal to 0, that is this quantity which I am circling. Okay. Why? Because no longer the Hamiltonian, the optimal Hamiltonian can be found by differentiating the Hamiltonian with respect to u, because the derivative on the boundary does not exist. So, we are including the boundary values of the constraint variable u. So, which means the following. So, how to approach? So, what I have is, so let me call this, so what I just said is the following. So, this is my relation A, this is my relation B and this is my relation C, and these are my relations, this boundary condition are my relation D. Okay. So, in my constrained optimization, what I have is that A, C, well what have I named? Yes, A, C, D, they are all set equal to 0 except now B. Now, so what to do with the condition number B? Now, we can not differentiate h with respect to u. So, instead notice that instead of partial h partial u, right, at the start condition they can be approximated as partial h partial. So, this partial derivatives we will approximate by a difference. So, this becomes the value at start condition plus u star plus delta of u. So, this is h at u plus delta u comma lambda star comma t minus h at x star comma u star comma lambda star comma t times delta u, right. So, what have we got here is divided by, so this is this times delta u, right. So, this times delta u is approximately equal to the difference, and what have we got here is that so let us now plug this back. So, let me call this as our condition B prime. So, using B prime in the relation for well, let me call this as 1, the relation for first variation of the functional. So, using B prime in 1, I see that partial, well, the first variation of the performance index is this difference, this is at u star plus delta u minus this is at u star. Okay. So, this we have to satisfy that this is greater than equal to 0, right. This is to begin with we had, and then from here what we get is, we get that h at u star is less than or equal to h at u star plus delta u. So, the final argument is that the Hamiltonian value at the optimal condition for the constrained optimization should be such that it gives me the minimum value in the neighborhood of the optimal control, right. So, the condition is as follows. So, let me denote u star plus the variation u to be equal to u of t, right, and I see that my minimum condition has now changed into an inequality, that this is bounded above by u, right, and this exactly is what I call as my Pontryagin minimum principle. Okay. So, I call this, well, this is the Pontryagin minimum principle. So, let me just state the necessary condition that we have found for the constrained control problem. The necessary condition for constrained control, for constrained optimal control problem, okay, or for optimal control problem should minimize the Hamiltonian, should minimize the Hamiltonian, and that is what my Pontryagin minimum principle states. Okay. Okay. So, let us now look at the solution methodology, starting with the statement of the problem. So, the summary is as follows. We start with the statement, given my plant condition x bar dot is equal to f of x u t and my performance index. So, these are my plant condition and my performance index, which is given to be j is s of x of t f comma t f plus integral from t 0 to t final v of x bar u bar t dt with boundary condition x bar of t 0 is equal to t 0 and x bar of t f is equal to t f is x f, and this could be our free boundary condition. Find, well, the statement is the same, find the optimal control, right, and so the solution methodology, the solution method is as follows. We will see that the only difference from our previous method for the previous description in case of unconstrained optimization is, now we are going to replace our equality where we optimize our control function with an inequality which minimizes our control Hamiltonian, right. So, step 1 is form the Pontryagin H function form the Pontryagin H function. So, H of x comma u comma lambda bar comma t, which is v of x bar u bar t plus lambda f of x bar u bar t. Okay. And then the step 2 is minimize h with respect to u, right, and we do that by so u now u of t. So, h with respect to the function u of t, which is bounded above by u, such that it satisfies the inequality h of x star u star lambda star t is less than equal to h of x star u. So, any other control parameter, control function lambda star comma t, right. So, we have to minimize by mainly looking at the boundary values. The interior values are found as we have done for unconstrained case. Okay, and then of course, we have solved 2n equations, the 2n Hamilton's equation. So, solve 2n state and co-state equations, 2n state and co-state equations given by x bar dot is equal to del h del lambda at star and lambda bar dot star is equal to minus del h del x at star, right. So, these are my 2n equations and along with the boundary condition. So, notice my control equation is missing because that has now been replaced in step 2 by the inequality. So, with the boundary condition again similar to the natural boundary condition that we had derived, right, and whenever we have fixed point boundary condition, they are replaced, they replace these natural boundary condition. So, this is at starred condition evaluated at T f times delta T f plus partial s partial x minus lambda bar again at starred condition T f delta x f is equal to 0, right. Okay. So, then the sufficient condition we will just briefly mention is identical to the unconstrained case, namely we have to check the second derivative of the Hamiltonian with respect to the control variable u, and that should give us and if the sign is positive, that should guarantee that we have found the minima. Okay. So, what I just said is the sufficient condition. So, condition so the sufficient condition for unconstrained problem was was to check for unconstrained problem was to just check the second derivative, right. So, that was what we have seen in our previous lecture was to check the sign of partial h partial u 2, right, and if this is positive, then we are guaranteed minimum, right, and for well. So, that was possible only for the unconstrained problem. The derivative, if u is found in the interior of the boundary, we can still take this second derivative, otherwise we will have to again resort to the Pontryagin function. At the boundary values, these derivatives are not available and these are not to be evaluated, right. So, these are only to be evaluated for constrained problem, the second partial derivative to be evaluated at at interior points. Okay. We cannot just justify the second derivative for the boundary points. Okay. Okay. So, let's look at some examples. So, I have a very simple example to begin with. The example says we need to minimize. So, I am given the h function. So, we need to minimize the scalar function h is equal to u square minus 6 u plus 7 subject to u less than equal to 2, right. And so, minimize the scalar function h subject to this constraint u, maximum value of u cannot exceed 2. So, if we if we were to differentiate, check that if we were to differentiate h with respect to u and set equal to 0, I am going to get u is equal to 3, right. So, that is not a viable solution because it exceeds our constraint, right. So, u equal to 3 is outside the constraint. So, then we have to check the boundary values. Notice that h at u equal to 2, if we plug u equal to 2, we are going to get minus 1, and h at the other boundary u equal to minus 2, we are going to get 23, right. So, of course, I see that u star is equal to 2 is my optimal solution, right. So, certainly we will not get the derivative equal to 0 at u star 2, but it gives my Hamiltonian to be the minimum value. Okay. So, optimal for the constraint problem. Okay. So, then let me wrap up the discussion of this part of the constraint optimization before giving examples by mentioning two other points. The first point is we have additional necessary condition, two additional necessary conditions, additional necessary condition. So, the first condition is if the final time T f is fixed, then I expect that the Hamiltonian does not depend on T explicitly, and in that case my Hamiltonian at the optimal value will be a constant. Okay. So, if the final time T f is fixed and the Hamiltonian h does not depend on T explicitly, then h of x star comma u star comma lambda star is equal to a constant, right. And this is for all t in T0 to Tf. Now, students should immediately recognize this additional necessary condition as our version of Beltrami identity, because if the Hamiltonian is independent of the independent variable, then we know that the Beltrami identity, from the identity the Hamiltonian becomes a constant, right. So, this is nothing but the Beltrami identity. And then we have another additional point to note, that if my final time is free and not specified, then the optimal Hamiltonian, and the Hamiltonian further does not depend on T explicitly, then in that case the constant is 0. The optimal value of the Hamiltonian at optimal control values is 0, right. So, what I have is the following. So, if the final time T f is free and not specified, free and not specified, the Hamiltonian does not explicitly depend on t, depend on time t, then I have that the optimal Hamiltonian is 0 in this case. So, that is a new set of observation that is to be found, right. So, if my final time is not specified, my H becomes identically equal to 0, that comes from the boundary condition, the natural boundary condition that we had derived. Okay. This is for all t from T0 to Tf. Okay. Okay. So, let us look at some examples. Well, at this point I have some examples at a slightly later point of time. So, in fact, now we are going to continue our discussion on this constrained optimization by looking at another form of the optimal control equations, right, and then we will look at some examples.